what I want to consider is the span of just the vector x. And what's the span of a single vector? Well, it's the collection of all of the scalar multiples of that vector. So like all of these things are in the span of x. So the span of x consists of any vector that's in the direction of x, in either the forward or backward direction, any amount. Do we agree? Okay. What I want to do is find, of all of those vectors, like of all of these things, which of those vectors in the span of x is closest to y? Right? It's probably not this one. This vector seems to be very different from y. It's probably not this one either. This one also seems to be different from y. Intuitively, it feels like it should be something like this. Do we agree? Okay. And so whatever the answer ends up being, the closest vector to y in the span of x, I will call the projection of y onto the span of x. Sound familiar? Okay. Here's how I'm going to make this precise. To measure how bad my projection is, I'm going to find the difference between y and my projection. So here's what I mean. My projection is of the form w times x, where w is the weight that I'm applying to the x vector to change how far I'm going. Okay? The error is the difference between y and xw. That's the error vector. Okay? And something that often confuses me is this vector supposed to point that way or this way? And the way I figured it out is if I added wx to both sides, it would be wx plus e equals y, which means I have to go wx plus e to get y. Okay, so it's this way, not that way. But e is the error. It's like how far, or it represents the gap between y and its projection into the span of x. And the goal is to find the w that makes e as small as possible. Right? I want to find the weight to apply to the x vector so that I make this error as small as I can. Right? So the weight shouldn't be super large. It shouldn't be all the way out here, because then this error is massive. It shouldn't be some tiny number like 0.001 either, because then the error would also be massive. So somewhere in there, there's a weight that brings wx as close to y as I can get it. And our intuition may tell us that the way to do it is by picking some w that makes it such that the error vector is orthogonal to wx. Note that being orthogonal to wx is equivalent to just being orthogonal to x, because they're in the same direction. Right? So that's our claim. The ideal error vector is orthogonal to wx. Okay? And remember, our goal is to just find the w that makes the length of the error vector as short as possible. Okay? And the length of the error vector is denoted as the norm of the error vector, but error is just y minus wx. And so what we're trying to do is find the w that minimizes this quantity. Okay? So in some ways, this is similar to what we were doing before with minimizing mean squared error. Like we chose a different w, we got a different mean squared error. Same kind of thing here. We choose a different w, we get a different length of the error vector. And we want the length of the error vector to be as short as possible. Okay? So our vibes kind of tell us that the error vector we're looking for is the one that is orthogonal to x. Do we agree? Let's prove that. Because just it feeling right doesn't make it right. Okay? So here's what I want to do. Let's recreate that picture from the previous slide, where I have y. We'll say this is x. And what I'm going to draw are two possible vectors in the span of X and see how far they are from Y. Okay, one of the vectors I will draw in the span of X creates an error vector that is orthogonal. Okay, and I'll call that vector W star times X. Okay, and if I use W star times X, well then the associated error vector I will call E star. Sound okay? So I'm saying, hey, one possible vector I could draw in the direction of X is the vector whose error vector is orthogonal. The vector whose error vector is orthogonal to it. I haven't yet shown that this is the shortest possible error vector. I want to, but I haven't yet justified that at all. How I'm going to justify it is by considering another vector along the same direction. Maybe I'll call this one W star X. Okay? And W star X will have associated with it its own error vector, which I might call E prime. Or sorry, this is W prime X. This was W star X. W prime X with it has associated an error vector, E prime. Okay, so W star X has the error E star. W prime X has the error E prime. Do we agree? Okay. And what I want to do, and let me just make this W prime X a bit more clear here. And my goal is to show, and that, this is a right angle, E star of X, E star is the shortest possible error vector. That's my goal. Haven't yet done it, but that's my goal. All right, and here's how I'm going to try and prove that. Maybe just to make this seem more rigorous, even though it's the same thing, I'll say prove. Okay? Here's what I'm going to do. What kind of triangle is this? Yeah, it's a right angle triangle because I chose E star because it's orthogonal to X. And what is the one rule you learned about in 7th or 8th grade involving right angle triangles? Yeah, the Pythagorean theorem. Okay, so what I'm going to do is take this right angle triangle and I'm going to redraw it out here. Okay? So it's the same triangle. Color it in. Okay? And what are the side lengths? Well, the length of this side is the length of E star. The length of the hypotenuse is the length of E prime. What is the length of this leg down here in terms of the stuff defined on the left? What is the length of this? It's the length of the difference between W prime and W star, right? It's however further W star is in this direction, W prime is than W star in this direction. So I'll call this the length of W prime X minus W star X. Okay? Using the Pythagorean theorem, gives us that, well, this squared equals this squared plus this squared. So the length of E prime squared is the length of E star squared plus this thing down here. Squared. And remember, my goal is to show that E star is the shortest possible error vector. That is, it has the smallest norm or smallest length of all error vectors I could draw when I pick some vector in the direction of x. Any ideas as to how I can come to that conclusion by using this equation? Like, why did I use the Pythagorean theorem? Yeah. Right. It has to do with the fact that the magnitude of w prime star minus, or w prime x minus w star x has to be greater than or equal to 0. Right? If w prime and w star are the same, well then this is 0, but otherwise this is greater than 0. Okay? So conceptually, I could think of this as being the length of E star squared is the length of E prime squared plus something. Do we agree? That means the length of E prime squared is the length of E star squared plus something. That something could be 0, could be greater than 0, but it's not going to be negative. That's more of a hand-wavy way of stating this. But the more rigorous way of stating this is that it just means that since this quantity here is greater than or equal to 0, it means that E prime's squared length is greater than or equal to E star's squared length. Now, what does this mean in English? What it's saying is that you can choose any w to multiply x by that you want. You are not going to get an error vector that is shorter than E star. Right? Because I didn't make any assumptions as to what w prime was. W prime could have been anything. Right? It could have, the picture I drew made it seem like it was further, w prime was greater than w star, but it didn't have to be, right? I could redraw the same picture if w prime only went up to here, or if w prime was over here. Right? Either way, I would just, redraw my right angle triangle, and the same analysis would hold true. W prime is any number that I could multiply x by. What this is showing me is that no matter what w prime you pick, it is not going to have an error vector that is shorter than E star. So what this is showing me is that E star is the shortest possible error vector. And how did I get E star? Well, I got it by finding the w star that makes E star orthogonal to x. So that's the big idea. If you want the length of the error vector to be minimized, the error vector must be orthogonal to wx. That is, the error vector must be orthogonal to your projection. Remember here, wx represents our projection. That's the key idea. I need my error vector to be orthogonal to wx. And how can I write that out algebraically? Yeah, remember, we looked at this last class. One way of expressing the fact that two vectors are orthogonal is that their dot product is 0, right? And so what this means is that I need to find the w such that the dot product between wx and E, it's kind of a messy x here, that dot product should be 0. I'm looking for the w that makes this happen. Well, let's solve. I know that E is nothing but y minus wx. Okay? Now, remember w, it's just a number, a single number, like 5. Right? And so what that means is, for the purposes of solving for the w that makes this equation hold true, assuming w is not 0, I can just divide both sides by w, so I don't really have to think about this first w. Okay? And remember, I could have started off just by saying the error vector has to be orthogonal to x, because x and wx are in the same direction. Okay? Now, we need to use the distributive property of the dot product to separate these parentheses. And remember, my goal is to try and isolate for w here. Like, I need to say w equals something. How can I do that? How can I isolate for w here? It's just a constant, right? The w is just a single scalar constant, which means I can pull it out of here. And I can write this as x dot y minus w x dot x equals 0. Okay? And what I can do is add this term to both sides to get x dot y equals w x dot x. Which means the w that makes the error vector orthogonal to wx is x dot y over x dot x. And since it's the best w, I'll give it a star, kind of like before. And so this is the w that makes the error vector as short as possible. Huge. You can see me telling the same jokes both times. He was here in the first lecture as well, for reasons that you will soon see. Okay, remind me, what is w here? Like once I plug in a vector x and a vector y, what does w star end up being? Is it a matrix, a vector? It's just a single number. It's a scalar, right? So to really make sure we understand how to use it, we'll try it out in practice in just a second. But just to recap, my question that I was trying to solve was, of all the vectors in the span of x, which of them was closest to y? I now have the answer. It's the vector w star times x, where w star is just this number. Okay? I didn't set it up this way initially, but it turns out that we just solved an optimization or a minimization problem, like the kinds that we started to solve way back in the first week of the quarter. There we were minimizing mean squared error. Here we're minimizing the length of the error vector. Okay, and it turns out that they're very related. Okay? So that vector, w star x, we call it the orthogonal projection of y onto the span of x. So to redraw our picture here, if this is y and this is x, w star x has been carefully chosen such that its error is orthogonal to x. So this is the minimum possible value of the length of the error vector. Okay, there's no other w that you could multiply x by to make the length of this error vector shorter. Okay? Now, physically, a useful way to think about what this orthogonal projection, w star, is as being the shadow that if you put a light on top of y, that you would see along x. That's why I've drawn it in black here. You can think of it as the shadow of y in x. Okay? Questions so far with what we've determined? Okay, so to really make sure we get what's going on here, I want us to work out an actual example with numbers. Okay? Here, I have two vectors, A and B, and I want to project A into the span of B. So the picture I should think of looks something like this. What is the orthogonal projection of A onto the span of B? Well, as I saw in the previous slide, it's in the form of some number times B, because vectors in the span of B are of the form some number times B. Okay? What is that some number? Well, we determined it on the previous slide. That some number, W star, is, in this case, B dot producted with A divided by, here's a question, is it A dot product A or B dot product B? That's why I intentionally used different variables here. So we couldn't just match it to the formula from before. Taryn. Good. It's the dot product of B with B. Why is it that? Yeah. The vector getting projected onto is the one that occurred 3 times in the formula. Right here, we were projecting onto the span of x, and there were 3 x's. Here, we're projecting onto the span of B, there are 3 b's. Okay? So, what is this number? Well, the dot product of B and A, it'll look like this. This times this plus this times this. I don't know why I drew a matrix there, it's a scalar. But it's negative 1 times 5 plus 9 times 2 divided by negative 1 squared plus 9 squared. This looks like negative 5 plus 18, that's 13. And this looks like 1 plus 81, that's 82. Okay? So the answer to the question is that the orthogonal projection of A onto the span of B is 13 over 82 times B. Okay, that's the concrete answer to the question that is highlighted here. Okay? So question. What is the orthogonal projection of A onto B? In this case, it's this exact vector. Okay?